Hello everyone. Today I'd like to talk about the Erdös distinct distance problem, which is a problem in Euclidean geometry that was introduced by Erdös, and which is about the distances between a set of points. So basically, you take a set of points in the Euclidean plane, you look at all the pairwise distances between points, okay? And you count how many distinct distances there are. And the distinct distance problem is to find the minimal number of distinct distances between a certain number of points. So more formally, if we have n points in the plane, well, we are looking for so we'll call it g of n, the minimal number of distinct pairwise distances between these points. Okay, so let's first look at small cases to see what's going on, maybe calculate g of n for small values of n. Well, when you have only one point, well, there are no distances at all. When you have 2 points, well, any arrangement of 2 points will only have one distance, so that's the minimum. Of course, the points need to be distinct, otherwise the problem is not very interesting. When you have 3 points, well, you just need to be a little bit careful. Of course, if you place the point anywhere, well, there will be 2 different distances. But of course, you can place the point in such a way that the 3 points make an equilateral triangle, so about here. And then there will still be one distance. Now let's show that you can't place a 4th point while still having one distance. So this is pretty simple. So let's suppose that we want to place a 4th point while still keeping only one distance. Well, then our 4th point must be at the same distance from this point and this point. Because of course, well, if it had a different distance to both of these points, we would already have 2 different distances. So since it's equidistant to this point and this point, it must lie on this line, okay? The line that's perpendicular to this segment, and it passes through the middle of it. Now we can say the same thing about, for instance, these 2 points. The 4th point must be equidistant to these 2 points, so it must lie on this line. Okay, so since it must lie on both of these lines, the 4th point actually has to be here. And even though my drawing isn't very precise, well, it's obvious that the intersection of these 2 lines is inside this triangle. And since it's strictly inside this triangle, well, we have found a second distance. Because, for instance, the distance between the 4th point and any of the points, so let's say this one, is strictly smaller than our distance, than our side length of the equilateral triangle. So, what we've shown with this is g of 4 equals 2. Why equals 2 and not more than 2? Well, of course, in our previous construction, our 4th point was equidistant to all 3 points, right? Because it lied perfectly in the middle of the triangle. So there's only a second distance that's created. There are no other ones. So g of 4 equals 2. And of course, before we had g of 1 equals 0, g of 2 equals 1, and g of 3 equals 1. Okay. So here we see that g starts growing as n gets large. So a pretty natural question is to try and see how fast G grows when n grows large. So this is what Erdös tried to do. He placed the first lower bound on the growth of G. So before looking at Erdös proof, I'll just do a short proof that sort of uses the same ideas, but doesn't prove an explicit bound. Basically, I'll just show that G of n goes to infinity as n goes to infinity. Okay? Basically, that if you take an arbitrarily large set of points, there will be an arbitrarily large number of distinct distances between them. So the proof of this fact is pretty simple. We'll just reason by contradiction. So basically, we'll suppose G of n does not go to infinity as n goes to infinity. Well, that means, since G is an increasing function, that at some point it must be stationary, right? Because an increasing sequence like this must either have a limit when n goes to infinity, or it must grow unbounded. So since it does not grow to infinity, it must have a limit, a finite limit. Okay, this means that for all n, G of n must be smaller than big M here. Because, well, if at some point it were larger, well, since it keeps on growing, it would not go towards this limit, right? It would be strictly above. Okay, so now that we have this bound, well, we'll try to show why it's impossible, why we must have strictly more than this number of distances when we have a very large set of points. So let's take n points. Okay, let's look at one of them. So let's call it point number A. And let's look at all the pairwise distances between point number A and all of the n-1 other points. So for instance, if I draw points here, 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 and some others, okay? Well, one pairwise distance is this, one other one is this, one other one is this, okay? And for each one of these points, I'm going to draw the circle of center A and radius the distance with the other point. So I'm going to get something like this. Okay? Now suppose that these are all of the distinct circles, but basically these are all of the distinct distances between A and other points. Well, that means that all the points that I haven't drawn yet must lie on one of these circles. Right. Now suppose we have, let's say, k circles. Well, first of all, observe that k must be smaller than m. Why? Well, because since we've taken a minimal set of points, a set of n points with minimal number of distances, well, we know that this number of distances is smaller than m. Now, we know that the number of circles is exactly the number of distinct distances between A and the other points. So, of course, well, this number is smaller than m. So we can't have too many circles. And now, well, since we have a lot of points, we're going to be able to argue that there exists some circle which has itself a lot of points. So here, simply by the pigeonhole principle, by pigeonhole, there exists a circle with at least n over k, with at least n over k points. Well, n minus 1 over k, sorry. Because we have n minus 1 points, all of the points except a, that we're dividing in k different circles. So, yeah. Well, now let's look at this circle. Let's not care about the rest, just look at this circle that has a lot of points. So here in our drawing, the circle with the most points is, well, there's this one with 3 points and this one with 3 points. So I'm just gonna, wait, no, this one actually has 4 points. So I'm just gonna leave this one. Okay. Now let's just cut the circle in two. So let's draw a diameter of the circle. And by doing so, we cut the circle in 2 semicircles. It's going to be clear very soon why we're doing this. Basically, since we have at least this number of points on the circle, well, we know that we must have half of this number on at least one of the semicircles. Once again, by the pigeonhole principle. Basically, here, since there are 4 points, we know that for any diameter that we draw, well, one of the sides is going to contain at least 2 points. So generally, so we have a semicircle with at least, so we have n minus 1 over 2 points. N minus 1 over 2k. Yeah, this bound divided by 2. But now the thing is, okay, here I'm just going to add a couple of points so that the next part is clear. So we're not going to care about the semicircles which has less points. We're just going to look at the one that has most points. Well, once we have points that lie on a semicircle, if for instance, okay, let's say you start here and you go clockwise and you take the first point, well, it's quite obvious that all of the distances between this point and other points on the semicircle must be distinct, because this distance is strictly smaller than this one, which is strictly smaller than this one, which is strictly smaller than this one. Okay, so we found quite a number of distances, actually quite a number of distinct distances. How many have we found exactly? Well, the number of points on the semicircle minus 1. So we have found n minus 1 over 2k minus 1 distinct distances. And well, now we're pretty much done. Why? Because since k is smaller than m, well, this number must be larger. Yeah, must be larger than n minus 1 over 2m minus 1. And this thing, of course, grows when n grows. In fact, this expression here goes to infinity when n grows. So in particular, we can say that this expression is going to be strictly greater than n. Okay, so that means that we can find n big enough so that by our proof here, we find too many distinct distances compared to the bound that we had supposed. And thus we obtain a contradiction. We cannot have such a bound, which means that g event here must be unbounded, and hence it must go to infinity. So okay, here I've explained quite in detail this thing. I spent a lot of time before even tackling Erdös proof, but it's because Erdös proof basically uses the same idea, just let's say in a slightly smarter way, to obtain some more precise, some more concrete bounds on the growth of G. So I'm going to go quicker on his proof now that I've shown the main ideas. So Erdös starts in the same way as we did here. He takes a set of endpoints with a minimal number of distances, and here's the first little trick. Instead of just taking an arbitrary point and looking at the distances with other points, he's going to take a point on the convex hull. Well, yes, a point that's part of the convex hull's of the border of the convex hull of the set of points. So to explain myself a little more clearly, let's say that our set of points is something like this. Okay? While the convex hull of this set of points would be this set. Basically, the convex hull of a set of points is the smallest, in the inclusion sense, it's the smallest convex set that contains all of the points. And instead of just choosing an arbitrary point like this one, well, Erdös, he chooses one point that's on the border of the convex hull. Why so? Well, because now notice that our argument with the semicircle doesn't even need to be done. Basically, when you look at all the distinct distances from this point to other points and you draw the circles, so okay, let's suppose these four are at the same distance somehow. Let's say these two are at the same distance. Okay. Well, now when you look at one of these circles, well, all of the points here, they already lie on the same semicircle. Why? Well, because if they weren't on a, well, if we can't find a semicircle that contains all of the points, it means that, for instance, we must have one point here and one point to the left of this line, so 1 point here, and then of course our set would not be our point here would not be on the border of the convex hull. So this is a little trick that lets us just avoid the semicircle construction. Okay, so to quantify exactly what we're doing here, well, we're going to suppose, so let's call this point A. Suppose that A has, so let's say big N distinct distances with other points. So basically, big N is the number of circles that you're tracing. If we compare to our previous proof. Right. Well, then there must be, so not only a circle but a semicircle, as we argued. So a semicircle with center A that contains how many points? Well, the total number of points left divided by the number of circles. So n minus 1 over n points. Okay? Now, by the same argument as before, well, we can find a point on the semicircle. So let's say the first one when you turn clockwise, such that all of its pairwise distances with other points of the semicircle are distinct. Okay, like we've got the same, system here, where let's say this is the point I choose at the beginning, or no, actually I'm going clockwise, so I would take this one instead. Well, this distance is strictly smaller than this one, which is strictly smaller than this one, and in such a way, well, we have found at least, so this number minus 1 distances. So really, it's the same thing as the previous proof, just that we managed to avoid the factor 2 here by looking at a point on the border of the convex hull. So now let's just finish this up. So recall here that our point A has n distinct distances with other points. That means that the total number of distances, okay, the total number of distances, which is of course g of n, since we've supposed that our set has the minimal number of distances. G of n, so it's larger than, well, it's larger than both the number of distances of our point A with other points, so n, and it's also larger than, well, this number of distinct distances that we were able to construct. So n minus 1 over n. And then that means, of course, that g of n is larger than the maximum of both of these values. And now basically, well, here, okay, n is our parameter from the beginning, so it's a fixed parameter, but here we don't know what big N value, what big N has for a value. It could be anything. But the cool thing is that this maximum here, well, is always larger than a certain value that depends only on small n. Okay, to see this, let's just sketch the function of both this and this when big N varies. So let's sketch. So of course here big N, so is just like this. It's just a linear function. So we have big N, and here we have n minus 1 over n, so it's like, it basically has the same behavior as 1 over x. So something like this, and here would be like this. And of course n is here, and here we have both of our functions here. Okay, and so we know that g of n is larger than the maximum of these two functions. And okay, so the maximum, it would be this thing here. So that means that in particular, g of n is larger than this value here, the value that's obtained at the crossing. Because if big N is smaller than this value for which we have the crossing, well then this factor here is larger, and g of n is in any case larger than the value of the crossing. And if we're afterwards, well then it's the linear function that is larger. And once again, g of n is larger than the value of the maximum at this point. So now we just need to find the value at this point, and we'll be done. I mean, we'll have our bound. So since this is the intersection point, it means that we have the equality n equals to n minus 1 over n. And I'm just realizing now, I forgot before, but there's of course a minus 1 here that I forgot to carry over from before. But of course this is not a problem here. The graph still looks the same, only that instead of here the function approaching 0 as n goes to infinity, it will actually become negative and approach minus 1. Okay? So we have this equality, and that means that we can easily find n as a function of small n. So basically, this big N that we're finding here is the worst case scenario. We're thinking in the worst case scenario, what bound do we obtain on G? And well, we'll say that in any other cases, the bound is larger than the worst case scenario bound. So here we have n squared equals to n minus 1 minus n. So in the end, we have the quadratic n squared plus n minus 1 equals 0. And I shouldn't be saying n all of the time because you're just getting confused between small n and big N. So I guess it's a bit of a shame. But hey, these were the notations used in Erdös paper, so okay. So let's just focus on this quadratic here. We'll just solve it quickly. I mean, there's no reason to waste time on these simple algebraic steps. So we have our delta, which is 1 minus 4 times, so minus n minus 1. So it's just 1 plus 4n minus 4, so it's just 4n minus 3. Okay, and we have our two roots for n, so we have for big N. So we have big N equals minus 1 plus or minus square root of 4n minus 3 over 2. Okay? Now, of course, here we must take the plus, because if we take the minus, we obtain a negative root. But here, of course, well, the number big N here, let's not forget, it's a number of distances. So it must be positive. It can't be negative. So we take the plus, and we have n equals minus 1 plus the square root of 4n minus 3 over 2. Okay? And so this is the bound that we obtain. Since, of course, we said that g of n, well, g of small n is larger than the maximum of these two values. In particular, it must be larger than big N. And and in the worst case scenario, big N is equal to this. So, g of n is greater than minus 1 plus square root of 4n minus 3 over 2. And now I'll just slightly clean up this expression to get the expression that appears in Erdös paper, and well, just to get a cleaner expression. Okay. So minus 1 plus square root of 4n minus 3 over 2. So this is just equal to minus 1/2 plus, so here we'll just factor 4. So square root of 4 times n minus 3/4 over 2. And now here you just split the roots. So this is equal to, so you have a 2 that comes out, it cancels out with this 2. And so in the end you have square root of n minus 3/4. Okay, so our final bound is g of n larger than square root of n minus 3/4 minus 1/2. Okay, so now, well, of course, we've obtained a statement that's stronger than just g of n goes to infinity. Here we've shown that g of n grows at least like a square root, basically. And so this is the first bound, well, the first lower bound on the problem that was proved by Erdös when he presented the problem. So, well, we're not going to go any further because showing any bounds that are better than this is, well, significantly more complicated. It was achieved little by little by other people, but I'll still show how this bound has evolved and what's the state of the problem now. So this is what we've shown, and now we have a much better bound. We have g of n larger than a constant times n over log n. Okay, so notice this is significantly larger than this. This is almost as large as n. But this fact is much harder to show, and in fact it was only shown in 2015, so rather recently. Of course, there are also quite a number of intermediate bounds that are in between this and at the same time smaller than this that were proved, that were proven over the years. Okay, so this is our current best known lower bound, and for the upper bound, well, the upper bound is much easier to find in a way. I mean, it's much easier to find a good upper bound. Why? Because you just basically, okay, here I'm not going to prove anything, but I'm going to sketch which set of points gives a good upper bound. Why am I saying that we can just find an upper bound with a set of points? Well, of course, if you take a set of n points, okay, and you show that there's a certain number of distances between them, well, then the minimum number of distance for n points, it must be smaller than the number we found. So it's actually very easy to find some explicit upper bounds. And the best explicit upper bound is given by points that are placed in such a way that they form a square grid. So for instance, here I have 16 points that form a 4x4 square grid, and here there are a ton of repeating distances, like this distance is the same as this, the same as this, the same as this. This longer distance is the same as this, is the same as this. Okay, so with all of these repeating distances, while you can calculate the total number of distances, it's not so easy, but it's doable. And you show that in this case, the distinct number of distances is basically a constant times n over square root of log n. And this is actually conjectured to be the right asymptotic, the right order of magnitude for g of n. Okay? In more technical terms, it's widely believed that g of n is equal to theta of n over square root of log n. Okay? And so, well, of course you can notice that the lower bound here that was proven in 2015 is really close to this upper bound. So basically, the problem is almost solved. There's only the square root here that has to be obtained. So yeah, it's really close to being solved, but we're not quite there yet. But hey, maybe soon. So yeah, that's pretty much it. I thought this was a cool problem, and you can get some results pretty easily. Although it's a very much still a current research topic, still somewhat of an open problem. There are also some variants. For instance, the problem in more than 2 dimensions, so in the 3-dimensional space or in an arbitrary number of dimensions. So many of these generalizations are still completely open. And so yeah, it's a fun little research topic that can be studied using simple tools, as we've done today.